Okay. Estimate the fin temperature at a distance of 5 cm from the base and the rate of heat loss from the entire fin. Now, I'm just going to, let's try and draw this out. So it says we have a long rectangular fin. Let me draw that first. And it's very important to note the word long in this question, because in our considerations of the tips of fin and the boundary conditions, it will be important to take note of that. So it says that this long rectangular fin is attached to a flat surface. So let's assume this is a flat surface. Okay. Such that the temperature at the end of the fin is essentially that of the surrounding air. So the temperature at this surface, as T infinity, has been given as 20 degrees Celsius. Okay. T infinity is 20 degrees Celsius. The width of the fin is 5 centimeters. So we have this to be 5 cm. Oh, sorry. The thickness is 1 millimeter. 1 millimeter. The thermal conductivity of the material K is equal to 200 watts per meter Kelvin. And the base temperature is 40 degrees Celsius. So the base temperature, as temperature at this point, is equal to 40 degrees Celsius. And the heat transfer coefficient is 20 watts per meter square Kelvin. So we have H is equal to 20 watts per meter square Kelvin. Oh, I'm running out of ink. Quickly get another pen. Okay. So the question says, estimate the fin temperature at a distance of 5 cm from the base and the rate of heat loss from the entire fin. So we're trying to find what the temperature will be 5 cm from the base. Let's say this is 5 cm. So at this region. Okay. Now, in order to solve this question, let us consider the conditions of the fin that we're trying to examine. Now, in doing this, you can consider the temperature distribution and heat transfer for fins of uniform cross-sectional area in 4 different ways. Now, first of all, you can look at, you consider if do you have constant temperature. Now, from all indications, we are just been given a temperature at this point at the particular time. You're going to lose energy from this fin. So we can't say we have constant temperature. Okay, it's not an adiabatic system. We haven't been told that from the question. So we can assume this to be an infinite fin length question. Okay, it's a long tip. because when you were deriving the formulas in class, you must have talked about a situation where you have a long tip. So you consider that to be an infinite length question. Okay. And we have a formula for getting the temperature distribution for an infinite length fin. And that formula is delta over delta infinite is equal to e to the minus mx. Okay, that is for the temperature distribution. And for the rate of heat loss, we have Q for an extended fin. We put here long fin is equal to the square root of this H PKAC delta. Okay, and we know this expression is just to show the temperature difference. T for the point of interest, and T infinity, and T for the base, and that's T infinity. This is equal to e to the minus mx. Right? I hope all these are not strange to you. I think you've done this in class. Okay. So these are the expressions that we
Can you get that a little bit better in focus?
Oh, okay.
It's in and out pretty bad.
Okay. I think this is shaking. Is this better now?
A little. That's good.
Okay. All right. So yeah, so this is these are the expressions that we're going to use to find the temperature at a particular distance from the base. And then we use this formula to find the rate of heat loss. Okay. Now, don't forget that you have to do some kind of analysis to find which formula to use for your question. Okay. It all depends on the initial conditions you're dealing with. Now, as usual, we are going to assume that steady state conditions exist. Okay. And the temperature loss in the fin is in one direction. To be a lot more complicated than this if we want to use the Cartesian three directional heat loss. We can also assume that the heat transfer is uniform in the fin. Okay. Now, if we do all that, then we can go right ahead and just plug in our values into these equations to find out our answers. Now, if you take a look at this question, we have been given K as 200 watts per meter Kelvin. This is an SI unit standard. But then we have been given the width as 5 centimeters, the length, distance as 5 cm, and the thickness as 1 millimeter. We have to convert those to standard units so that everything goes smoothly. So our width is equal to 5 cm. If you convert this to standard units, you get 0. Just divide this by 100. You get 0.05 meters. And then the thickness, which is 1 millimeter, divide this by 1,000. You get 0.01 meters. And our point of interest, I'll call that L, is also 5 cm. And we also get that to 0.05 meters. And the expression for M is the root, these are all formulas that you find in your textbook, okay? Multiplied by the area of convection, okay? And we have H to be 20 watts per meter square Kelvin. And this is multiplied by the perimeter. Now, the perimeter of the fin, okay, we'll just multiply the width by 2 and then add it to the thickness multiplied by 2 just to get the distance around the fin. Okay, so this is 2 multiplied by, putting all this in one bracket, 0.05 meters plus 2 multiplied by 0.01 meters.
Can you move the paper up real quick?
Oh, sorry.
Thank you.
Took my eye off the screen. Sorry about that. Yeah, so all this now divided by, we have a value for K, which is 200 watts per meter Kelvin. And then the area of convection. Now, let me just explain that real quick. Imagine that you take a cross section of this at this point. Let's say we cut this off and we're looking at it from this direction, okay? We're going to see something like this. We're going to have 5 cm by 1 millimeter, okay? And that is the area of convection, all right? So we're now going to multiply K, which is 200 watts per meter Kelvin, by 0.05 multiplied by 0.01001 meter square. And let me pull my calculator out real quick. Okay, so 20. Let me do the perimeter side first. So 0.05 multiplied by 2. 0.05 multiplied by 2 plus 2 multiplied by 0.01001. We get 0.12, and if you multiply that by 20, we get 2.04, all divided by 0.05 multiplied by 0.001 multiplied by 200, 0.01. Are you evaluating this on your own? What do you have?
My answers line up with yours.
What do you say?
That looks right.
Okay. I know I'm getting a very large number, which seems incorrect. Okay, let me take this one by one. So 2.2 multiplied by 0.05 will give us 0.1. 2 multiplied by this will give us 0.02. If we add that together, we get 0.01 plus.
Hey, Vincent.
Yeah.
Is that 0.001 supposed to be 1 centimeter?
No, the question says 1 millimeter.
Okay.
Yeah, except if that's a typo.
I think what we're missing is the square root after that really big number.
Oh, yeah. Thank you very much. Yeah. Okay, so if we do that now, get yeah, that's more like it. So this gives us square root of, if you divide this, you get 204, and do that, you get 14.8.28. Okay, and this is that. Now, usually, I'll try to cancel out most of the units just to see. So you can see that this goes with this. This goes with this. This goes with this. And yeah, we have another M here. No, this is just one M. So I'm looking at the text, and we have one M left at the bottom. Anyway, this is the unit for our expression. And once we get this, we can then put it in this formula right here just to find what the temperature will be at that boundary, which is T. Okay. So if we say T minus T infinity, we know T infinity to be 20 degrees, because we're told that this shares the same temperature as surrounding air. So say 20, and then the T for the base is 40 degrees. So 40 minus 20 exponential minus 14.28 multiplied by the distance that we're considering, which is 0.05. Okay. 0.05. Okay. So now let me evaluate this exponential first. 14.28 multiplied by 0.05. Put that down. Okay. We get 0.714. Okay. I'll multiply that by -1. Oh, sorry, 14.28. 05. Okay, and then just we can take all that. The difference between 40 and 20 is 20, right? So just do that. So that would be -714. Is that correct? I'm struggling with this calculator. Can you please evaluate this for me, please, if you have a good calculator? And then multiply this by 20. What do we get?
The exponent times times 20. After you do all that, that'll equal 9.79.
Okay, so we get 9.79, right? Okay, and then if you add this to 20, we get T to be 29.79 degrees Celsius. Okay. So that would be the temperature at this given point. Okay. Now, the rate of heat loss, we also have a formula for that, which is this. Okay, so Q is equal to the square root of H multiplied by P, K, AC, and delta B is simply equal to just the difference between the base temperature and the temperature at the infinity point. So I can replace that by TB minus T infinity. Okay. So this is simply square root of, we know H to be 20 watts per meter squared Kelvin, multiplied by the perimeter. We already evaluated that here. Okay. So 2 times 0.05 plus 2 times 0.001. Okay. And then multiplied by K. K is, we're giving K to be 200, this is meters, 200 watts per meter Kelvin. And then we'll now multiply this by the area, which we already know also to be 0.05 multiplied by 0.001 meter squared. And then all this now multiplied by the difference in temperature between the base and infinity, which is 40 minus 20. Okay. That's a lot of terms. But can you quickly evaluate that and tell me what you have? Do you have that? 20 by 2 times 0.05 plus this times 200 times this times 20.
I got 2.856.
So 2.856. This is a rate of heat loss, so watts. Okay. So don't get confused by this question. I think the most important thing to note here is which formula to use. And the analysis, the thinking behind this is we're considering the temperature at a point and in the middle of our fin. So this qualifies as an extended tip, a long tip, okay? And once you come to that conclusion, then the formulas to use are you just have to pull it out of your textbook. Okay. Now, we have another question. The second question says, a 20-meter long, okay, let me draw that. 20-meter long and 8 cm diameter hot water pipe. So we have a pipe. That is 20 meters in length. And we have a diameter as 8 centimeters. Of a district heating system is buried in the soil 80 centimeters below the ground surface. The outer surface temperature of the pipe is 60 degrees Celsius. So this is 60 degrees Celsius. Taking the surface temperature of the earth to be 5 centimeters. Okay, so this is buried. Let me just draw this. So, okay, this is a pipe that is buried on the ground. No, so I think it will be buried parallel to the ground. Let me just consider. Okay. So the surface temperature is 5 degrees Celsius. And the thermal conductivity of the soil at that location is 0.9 watts per meter Kelvin. So the soil surrounding the pipe has a thermal conductivity of 0.9 watts per meter Kelvin. Determine the rate of heat loss from the pipe. Okay. It is buried 80 cm. So we have this. Let's say this is a cross section of the pipe. Distance from this cross section to the surface will be 80 cm. Okay, so let's take a look at this now. Let's just do a quick analysis. If we have heat transfer, let's say we have some kind of fluid going through this pipe, and the temperature here is 60 degrees, the temperature here is 5 degrees, a gradient is established, right? Heat is going to be lost in this direction. But heat has to first of all go through the pipe before it is lost to the ground. Okay, let's say this pipe has a thickness. Okay, so hot water is flowing through, but the heat has to go through the walls of the pipe first. And if you remember, when we were talking about the types of axis of analysis, we talked about cylindrical coordinates, we talked about spherical coordinates, and then we talked about Cartesian. So heat is going to be lost from the pipe to the ground. To analyze that properly, you have to use cylindrical coordinates before you assume that, okay, the heat loss in the ground will be your regular Cartesian coordinates, okay? Well, in this case now, I don't think the question is asking us to find the heat loss through the pipe. We already know the temperature at the outer side of the pipe. Okay, we are not considering the temperature inside. We already know what the temperature will be on the outside. Half of the work has been done for us already. So we just have to consider how much of that heat goes out. However, this is a boundary layer problem. You have to be careful the assumptions you make. Okay, and there's a consideration that we have to do when we have boundary layer problems like this. That has to it revolves around heat loss from different shapes. Let me call it that, because the structure of the soil is different from what the cylindrical pipe will feel like in the soil. So the interaction between the pipe, if we're looking at it from this direction, will be something like this. Now, once the heat gets to this point, it's almost a one-dimensional heat loss. But around the pipe, the nature of the heat loss around the pipe is not it's not one-dimensional. You have something like this. Okay. I hope this makes sense to you. Okay, you're going to lose heat, something like this. So in boundary layer, there's something called the shape factor. Okay, the shape factor that is used in boundary layer flow is just to help differentiate between how the heat is lost, considering if it's a laminar or turbulent flow. Okay, it shows up in different treatments of boundary layer problems. Okay, and in this question, if I don't know if you've done this in class, well, if you consider the thickness, the depth at which this pipe exists, and the the thickness or the diameter of the pipe, then you see that 80 cm, let's assume that that's our depth, right? Okay, let's assume that to be Z. It is greater than 1.5 the diameter. So from your textbook, if you check, I think it's table 3.7. Can you confirm that for me if you have the textbook? Because I'm not sure if I'm using the older version. Okay, you have an expression for the shape factor, which is S equal to 2 pi L natural log of 4Z divided by D. Okay. Now this accounts for the fact that we have a weird shape in what would have been a regular just 3-axis problem. I hope this makes sense to you when I'm explaining it. Anyway, so taking into consideration the shape factor, we've been given the length of our pipe. Okay, we know the depth, we know the diameter, and so we can find the shape factor. Now, this shape factor is added to the calculation of the heat loss just to account for this change in shape. Okay, because our heat loss equation becomes T1 minus T2. Right? Now, this should be a regular expression, but we're taking consideration of this. So you can see that it's just a simple formula question. If you use the formula, you find your answer. So once again, it just comes down to knowing how to choose the right formula, doing an analysis. Sometimes it pays to actually just talk to yourself, have a conversation in your head and just say, okay, how is the heat loss going to happen? Okay. And as you solve more and more questions, you become more flexible in making those finalizations. Okay, so S is now equal to 2 multiplied by 2 pi into 20 meters. Natural log of 4 multiplied by 0. Once again, be careful not to mix your units up. We have 0.9 is given to
Excuse
us.
me.
Yeah.
What table in the book did you mention
I'm
for the
sorry.
shape factor? The table?
Yeah. Yeah. What did you check that?
No,
It's,
what was it again?
Table
The table.
3, table 3.7 from chapter 3. Table 3.7. Did you check that?
Yeah, that's correct.
Okay. All right. So yeah, it seems like they haven't changed anything in the new edition then. They haven't changed that rather. Yeah, so so as I was saying, don't mix up your units, okay? Just you've been given this watts per meter Kelvin. It is easier to change these to the standard units than to change this to match this. So 80 cm becomes just divided by 100, we get 0.8 meters, okay? And then this is going to be divided by natural log affects all of them. Divided by the diameter, which we had as 8 cm. If you divide it by 100, you get 0.08 meters. Okay. All right. So can you compute this real quick? Let's see what we get. Were you able to compute this?
Sorry, I was writing stuff down. I'm computing it right now.
So that's 4 times 0.8.
Okay, for S, I got 34.06.
Okay. Okay, so we'll just put that value, just plug it in directly. And then what do you get for this one?
And then that will be 1,686.
Okay. So that would be the heat loss for that question. Do we have time for one more question? Okay. So looking at this question, and it seems like it's beyond the scope of this class, but I'll be surprised if you guys have done this in class. So it says metal plates with a thickness of 1 cm are being treated in an oven for 2 minutes. Okay. Air in the oven is maintained at 800 degrees Celsius with a convection heat transfer coefficient of 200 watts per meter squared Kelvin. If the initial temperature of the plates is 20 degrees Celsius, determine the temperature of the plates when they are removed from the oven. Okay. Okay, so metal plates, the stats for the metal plates are given as K. Thermal conductivity is 180 watts per meter Kelvin. Density 2,800 kilograms per the cube. Yeah, CP to be 880 joules per kilogram Kelvin. Okay, and then the thickness is given as 1 centimeter. You can immediately change that to 0.01 meter. Heated in an oven for 2 minutes. Okay, let me put this, I can put T equal to 2 minutes. Should be 120 seconds. And the oven is maintained at 800 degrees Celsius. So air in the oven is, put this oven 800 degrees Celsius. If the initial temperature of the plates is 20 degrees, plates temperature is equal to 20 degrees Celsius. Determine the temperature of the plates when they are removed from the oven. Now, this question, if you're heating up plates in an oven, then you have to know how much of this energy you're losing, how much of the energy is being retained by the plates, and how much of the energy is being lost to the environment, to the walls of the oven. Okay, and in the question, we've also been given the properties of the walls of the oven. Okay, and those are given as density is equal to 1,920 kg per meter cube. We're given Cp to be 700 joules per kilogram Kelvin. And then we have K to be 0.9 watts per meter Kelvin. Okay. Now we can find the characteristic. Have you guys done Biot number in class? The characteristic Biot, characteristic length, which considers Biot number.
Yeah, we've talked about it.
Oh, okay. Yeah. All right, so we have the formula for the characteristic length to be this, right? So I guess I actually haven't done this in a long while, this particular question, which is why I'm surprised that you've done it in class. Okay. So we know the length of hold on. I'm just trying to verify that we have the right values here. Well, I'm looking at this and I just can't seem to find the connection between the solution we have here and the question. Because if you're looking at the characteristic length of the brick wall in the oven, then surely you have to consider that the Biot number depends on the dimensions of the oven, and that has not been given in the question. Okay, except if the question is incomplete, because we haven't been given any dimensions for the oven, right? I just read the question, I can't find it. Yeah, that question seems incomplete. It's question 417. Can you please take a look at that question in your textbook and see if there are dimensions actually given in the question for the oven?
You said 417, right?
Yeah. Yep. Do we have dimensions there? Because we have to find V, right? And
In class, we use the volume of the rods, not the oven.
Oh, really?
Yeah, we use like a metal ball, but yeah.
Okay. Okay. I mean, we've only been given the thickness also. So how do you find the volume of the rods if you only know the thickness? I'll be surprised if that was the case. So is that the, can you read question 417? We're almost out of time. I just want to see, I'll probably check it up later.
Yeah, metal plates with all our given K,
Mhm.
rho, and C sub P values, with a thickness of 1 centimeter, being heated in an oven for 2 minutes. Air in the oven is maintained at 800 with a convection heat transfer coefficient of 200. If the initial temperatures of the plates is 200, determine the temperature of the plates when they are removed from the oven.
Okay. Wow. Okay, I'm going to take a look at this and then I'll get back to you. Okay. I think next week I should be able to explain how to move forward with this without dimensions given. Okay. Sorry about that. Yeah, it's been a while I did this myself, which is why I'm surprised that you're doing it in your undergraduate class. Anyway, so that's it for today. Sorry we weren't able to move ahead with this question. I apologize for that, but I'll definitely find an explanation for that for you next week. Okay. All right. So yeah, have a nice rest of your day and see you guys next week.
So yeah.
Thank you.
Yeah.